Hi, my name is Nabilah Binti Muhammad Nabil.
And hi, my name is Zuhaidah Binti Dzulkarnain. So we're going to present our project which is titled Minimization of Logic Circuits.
Okay, so since our project title is Minimization of Logic Circuits, so first I'm going to introduce to you what is logic circuit. So basically, logic circuit is a collection of logic gates, the input signal that drives them, and also the output signal that they produce. And the major use of logic circuit is actually in digital electronic computers, as you can see here. Logic circuit actually consists of two types, which is combinational logic circuit and also sequential. But for this project, we are only going to discuss about combinational, which is a logic circuit without a memory. So as you can see here from the slide are a few types of IC. So what is IC? So basically IC is an integrated circuit where logic circuit is in an IC. So in an IC there is a logic circuit in it. So basically all these logic gates that connected in the IC will give an output based on the circuit connected inside the IC. And the output of this is used to perform a specific intended task. So the IC that we are going to discuss in this project is SSI, which is small scale integration, where in one IC we can fill up to 12 gates. Okay, so next we're going to look at the objective of minimizing a circuit design. So a circuit design can be really complicated when we combine different type of logic gates and different type of ICs. So a simpler circuit design is actually more desirable because it contains a fewer number of gates. So when we use least number of gates, first it will reduce the cost of the hardware, and then it will decrease the power dissipation, which means less heat will be produced. And when we use less logic gates, actually the most important part is actually it will increase the speed of the circuit. It will increase the overall speed of the circuit. This is because less gate, meaning that the input will propagate to less layer of logic gates, which means that the circuit will operate faster with a few layers of gates.
Okay, next we continue with the literature review. In 1978, Z. Kohavi defined the minimal circuit as the one that uses the fewest numbers of logic gates. The purpose of minimizing logic system is to identify the simplest form of a system by removing all the redundant elements. The purpose of simplifying the algebraic expression of a Boolean function is called minimization. In this expression, any element that can be removed from the equation without changing the input and output relationship is categorized as the redundant elements. Circuit minimization is very important to reduce the implementation cost of the circuits and its complexity. The implementation cost can be reduced by reducing the numbers of elements in the circuits and minimizing the combinational logic portion that produce the output.
Okay, so next proceeding is the problem statement of our project. So as you can see here from the slide, a logic circuit designed by the company X, and company X wants to design a logic circuit with the minimal use of IC, and we need to analyze whether the design of the circuit is minimized or not. Okay, so now I'm going to talk about the method that we use to solve our problem of minimization of a logic circuit of company X. So basically we have 10 steps, but right now I'm going to explain in general of what we did. So first, from the logic circuit of company X, we first analyze it by taking out all of the logic gates inside each of different IC, and when we did that, we draw a new logic diagram. So when we draw a new logic diagram, it is easier for us to identify the Boolean expression through the logic diagram. And when we have the Boolean expression, what we did is we simplify the Boolean expression first, and then we draw a truth table from this Boolean expression. This Boolean expression we simplify using De Morgan theorem and also Boolean expression simplification. So after we did that, we then minimize some more the Boolean expression using K-map. So right now, we get the new expression from the K-map is the most simplified version of our logic circuit. So when we have this simplified equation, what we did is we draw a new logic diagram from the simplified equation. So basically, this new logic diagram is the minimized version. So to prove whether this minimized version is correct or not, what we did is from the new equation, the simplified equation, we draw a new logic truth table. When we draw this truth table, we compare between the unsimplified version of the logic circuit, which is the original logic circuit truth table from company X. We then compare it with the simplified equation that we did through Boolean simplification and also K-map to prove this. Okay, so the reason why we did this comparison of truth table is because one truth table actually can have many different logic equation and also logic circuit can be found from one truth table. So basically different logic equation and circuit can exist for a given truth table because it is always possible to add or unneed or redundant logic gate circuit without changing the logic output. So this is why we compare between two truth table, which is the original from company X and also the simplified version that we did through the K-map.
Okay, basically this is all the result and analysis that we identify in this project. As you can see, the original circuit is more complex and use many types of ICs that contain different types of logic gates as compared to the minimized circuit, which is used less numbers of the logic gates and the circuit is more simple and direct. This method was proven by comparing the original circuit truth table and the minimized circuit truth table. What we identify is the output of these two circuits is completely same, which means this method can be used to minimize the original circuit without changing the original output. As part of the analysis process, this is the result of simplification of the Boolean expression that we identified in this project. In this part, we need to simplify the original Boolean expression that we identified from the original logic diagram. After the simplification process, the result of an expression need to be minimized by using the K-map table. This is the expression that we identify after minimize the circuits by using K-map. As a discussion and conclusion in this project, the new expression that was obtained from the result was used to implement the new circuit that is equivalent to the original circuits. Through the method that we apply and the result that was obtained, we are able to minimize the logic circuit of company X, which is result in less cost, increased operational speed, decrease the power dissipation. The logic circuit designed by company X has been minimized successfully and the method used to minimize the circuit is proven.